Hello, everyone. Thank you to be here. It's really a pleasure for us to speak today at the Vox UK. So today we're going to bring you some, I will say, some special use case using Elasticsearch. We will show you how we use this technology and many others to explore large graph at the heart of the French National Audiovisual Institute. I want to ask you already, who knows what the French National Audiovisual Institute is? Because there is no one from France.
That's good.
I'm gonna explain it just later, but first thing first, we work in a company called Adeline. It's always hard to pronounce the name. We never know the pronunciation if it's Adeline or Adeliane. Essentially, we are experts in search technologies. As I said, we are experts mostly in Solar-based search engine, like Elasticsearch, OpenSearch, and Solar. We offer consulting and training. We like to speak at conferences, so we really love to share our expertise. And we develop our solution for e-commerce that is called A2, or A2 in French. We also develop our own search engine called Odosite. So it's a bit different from a classic one. It's a collaborative search engine. And that's it, the French National Audiovisual Institute. So I can tell you more about it. I'm going to call it INA from right now, because it's just too long to pronounce the entire name. So the INA, it's a French public institution, and the goal is to preserve the cultural audiovisual heritage of France. So essentially, what we are doing is collecting every TV and radio program 24/7 and storing it, and give the access to some of the content to the public and some other content to the documentalists, so for internal usage. Well, I think we should have updated the slide, but we are around 22 million hours of recording. We also store photos, can be digital photos or also physical photos that we can touch. And we are not storing only the traditional media. We are storing also the web. So we have 16,000 and so it's growing archived websites for 100 billion URLs. We are also storing tweets. Can I call them still tweets, even if it's not Twitter 6 now? Okay, fine, thank you. Why we are storing tweets? We are not storing all the tweets of X. We are storing tweets following a certain hashtag, or we are that are related to France, of course. Or we are storing tweets from French personality or personality that are related to with France. What else are we storing? We are storing also Netflix. Once again, you will ask, why you are storing video from Netflix? What are you storing? Are you storing, I don't know, a TV show on Netflix? There is not The Last of Us, but, well, it's another thing. We are doing it for French-related media. Like, for example, there was a TV show about the Olympics in Paris, so we are storing that as well. So we have a lot of data. And with my colleague Radu, I forgot to present ourselves, sorry. So I'm Pietro, and yeah, my colleague Radu, sorry. We work into the data lake project with our many other colleagues. That's also thanks to them if we are here today. It's a project that started around 10 or even probably more years ago. Time goes past really quickly. So the goal of the data lake essentially is to store all the metadata, so the information related to the content that we store at INA, and to make it available, once again, for internal usage or also for public usage. And it's a classic 3-tier architecture, so we have 3 different layers. We have a layer for storage. We have heterogeneous databases. Since it's a data lake, we have everything. We have SQL, MariaDB, Postgre. We have NoSQL, MongoDB. We have Elasticsearch. We have too many versions of Elasticsearch because we are migrating. We are still using version 5. And we are migrating soon to version 7, to migrate soon to version 8, and probably to version 9. Probably we're going to have also some OpenSearch. So we have many databases. We have a processing layer, of course, because data are moving sometimes from a database to another, and we need to transform this data to adapt it for the nature of the database. And of course, we need also to synchronize data between each database. And finally, we have also our management layer. The management layer is, for us, the most important because we work on search engine, so it's the place where we work. And also, we have not only the management for search, but also for monitor, because we have to be sure that everything is working correctly, of course. So the data lake project, you can see there the lake. You have many kind of data inside this lake. Too many kind of data, probably. So we have, I'm going to start from AI-generated data. We're not going to talk much about AI today, but it's something quite important in our let's say, everyday life. We have, for example, we have transcriptions. Transcriptions, why? Because as we stock every radio and TV services, we also transcribe them because we may use it for search, for example. We also have diarization for transcription. We have face recognition because we want to know if in this program there was Macron or if there was, I don't know, some other politician or the new Pope. And we have also some other AI-generated data, like we use also techniques of named entity recognition to find entities into our transcription or into our descriptions, because programs comes, of course, with a description. We also have embeddings for semantic search. In this case, we use dense vectors. We are working a lot on this recently. It has been a year that we are working on hybrid search. So hybrid search is like a combination of lexical and semantic search. And we're going to soon present our work at another conference. I don't know if I can say the name of the conference, or I won't say it. We're gonna why it's really important for us, because we are transforming transcription data and video as well into embeddings, so into a embedding format, in order to perform semantic search on this data, so to discover all the documents that doesn't contain enough metadata to be discoverable. Then we have, of course, logs. And finally, I won't talk too much about logs because, well, I don't know. They are interesting, but maybe less than the other kind of data. And then we have, of course, metadata. For metadata, this is used to describe around 60 million documents. So when I say 60 million documents, I don't intend the document in the JSON sense, but the document into into INA, essentially. So metadata is used to describe them. And to give you to make you understand the complexity of all this, we need, of course, to talk about the data model. So first thing, into our data model is, of course, the content. So the content can be a video or an audio, can be images, can be text. So you can read, we have, for video, for example, we have the TV news, we have the documentary, we have the movie that went on TV last night. Then, associated to the content, we have event. What kind of event? Well, we have the event of conception, when the movie was created, or the TV news was created. The event of production, the first release, the broadcast, and of course, there can be multiple broadcasts for the same content. And then we have the media. And the media is the physical object that contain, or the digital one that contain the content, essentially. So you can see we can have tape, file, or archive. We can, or we have to store essentially the same content sometime, multiple time in different media. Because, for example, there may be a new codec, and so we save the content in multiple times. To give you an example here, so here we have the TV news at night. So the content is essentially the TV news. But the TV news, for example, can be broadcasted multiple times. Can do eye to the camera. Can be broadcasted multiple times. Like we have the TV news in the morning, the TV news in the afternoon, in the evening, the day after, the day before. So we have different events associated to the same content, essentially. Oh, sorry. Just
the other way around.
Yeah, the other way. And then everything goes even more complex, because to each of this entity, so we can see here the different entities, so the content, the event, and the media type. We have metadata associated. Metadata that can be of two different kinds. So we have the free text that comes essentially with the entities. For example, the title of the movie, or the summary of the TV news. And then we have curated data, where our documentalists add informations. So we can have, for example, concepts that are added to our entities. Concept can be, for example, where the movie was taken. Like, I don't know, Harry Potter was in London, so there may be a concept related to the entity Harry Potter. It's this way. So this give you, this is big, but it's simplified. It's a simplified version of something that looks like a large graph. And we have to struggle to work with this large graph. And I'm going to let my colleague Radu tell you more about this. You want to stay there?
Yeah. So I guess you got the idea a bit of what kind of data we are handling inside our data lake project. I just want to emphasize on the fact that we are talking about metadata, so not the content, not the video, not the images themselves. So they are stored separately, and our role is just to facilitate the access, the search of the metadata. So in terms of use case, for us, it's a very interesting use case because of the complexity of the data. I used to say we have lots of data, and it's a big repository, but size it's relative. In terms of content, we don't store. In terms of metadata, we don't store petabytes of data. But the relations in between different concepts and entities are quite complex. So that's why it's interesting for us, because it's a challenge to make to extract all these relations and to use them further on in the search engine. There was a very interesting presentation earlier on about classification, categories, subcategories. So once you get into that domain, you realize that it gets very complicated, very easy. Anyway, we had to come out with a formal model to try to accommodate all these descriptors of different heterogeneous content. And we came up with this graph. We didn't reinvent the wheel either. So we were inspired by the cultural heritage models with you have different specific entities like instances, credits, events, concepts, so simple things. And the goal of this model was to be flexible enough, generic enough to accommodate the evolution and eventual other categories of things that might come in the future. I used to take the example of the news that are systematically captured and stored each and every day. But let me try to extrapolate this one with a simple and more intuitive example. If you take, for instance, this conference, Divox, you can imagine that this is the central instance. Imagine Devox, the conference, it's associated to an instance. Then you have different events associated. You have Devox 2025, you have the previous versions, 2024, and so on. So there is a relation in between an instance, and there are different events associated. Then you have some items maybe associated to the conference. For instance, the recordings, the videos that are associated to each event. And for each instance, you have a certain number of participants. You have credit, annotations, different relations in between speaker, presenters, organizers. There are different agents that are related to a specific event. Different concepts, you have places, you have subjects and tracks, different topics that are debated during the conference. So you see, with a simple model here, it's a simplification. I won't get into detail on each and every box on the schema, but the idea was to show that with a semi-structured data and a variety of things and descriptors, your model has to be very generic. And that's the beauty of it, because if it's very generic, then you try to squeeze it and to put in a search engine. And this is where the most difficult part is. As Pietro mentioned in the beginning, we have everything in a relational database. Okay, straightforward. You have the tables, different relations in between each tables, and you have millions and billions of items in the relational database. Then, of course, you can use you can interrogate the database, SQL queries, and you try to do your joins and different combinations and different filters. But in terms of usability and access is not the best option. Another possibility is to try to transform or to do extrapolation of different views of this data, of this schema into a document view. But then your documents could be very complex, very deep, very long level of imbrication in between different parts of the document. So this is where it becomes complicated to put it in the perspective of a search engine. And again, our objective in the group is to provide access to the content, to provide search facilities, and one of the best ways to do that is to use the text description of different elements. So we are trying to flatten the graph representation of the metadata into flat documents. One idea and one hypothesis that we came out with was to imagine that we won't store everything in the same place. So we defined it different points of view, different cuts and different selection of entities from this graph to be represented, stored, and accessed according to the different functional points of view. So, for instance, here I won't take into account all the events and all the conferences, for instance. I will have a separate index, a separate part of my collection that regroups only concepts. For instance, places, cities, countries in the world, different ontologies and different classifications of video and audio content. So we have this functional view of the concepts. Then another grouping and another point of view on the graph would be to put together the instances with their events and their regroupment of different instances, and so on and so forth. We can simplify and have different slices of this graph into specific indices, and that would allow us to simplify the structure of the documents afterward. So that being said, we have, or at least we defined the model of our documents. Now the first action to be done was to index them into a search engine. As we mentioned, the choice was initially made for Elasticsearch, and the indexing workflow is quite straightforward. As we said, we have different databases, heterogeneous sources, because different departments have different technologies, different modeling, and so on. And there are different steps of migration, curation, transformation of the data. So all this is not necessarily our main focus on the workflow. And everything, we can imagine everything starts from our PostgreSQL, from our relational database, and we shift everything directly to Elasticsearch, JSON documents, everything is nice, straightforward, and then we can build a search engine on top of Elasticsearch. So we put that in place, the whole framework, indexing, all the SQL queries in PostgreSQL, all the sophisticated relations and transformations that were required, the schema to be used in Elasticsearch, all the indices and everything. And everything is fine. We launched the indexing process for the whole data set, and everything lasted for 3 weeks. So it was fine. We achieved our goal to have the whole content, the whole metadata in our search engine, to build a search engine on top of this. But the problem is that this kind of workflow should be reasonable in terms of processing and in terms of time, because not only the volume, it's increasingly growing and growing from one year to the other, naturally because we have more content, but also there are updates on different parts of the documents. So when you put all together, it's not feasible to have a certain a system that takes so much time to be updated and to be initiated. So that was one optimization that we had to consider along the way, to do a pre-processing of the documents, which is to say, instead of starting from the relational database and for each instance, for each document, to have a very complex SQL query that will take a certain amount of time, so several milliseconds, several seconds, tens, minutes, and to iterate that 60 million times, we decided to pre-calculate fragments of this final document. So instead of produce the global document in one step, each part of the document was prepared in a preliminary phase. And this is what we call the fragments. So we have essentially fragments of the JSON documents that are temporarily stored in a MongoDB database. And then the final indexing phase will be much faster, because in the final Elasticsearch document is just a combination of fragments that are already computed. So doing that, we reduced with an order of magnitude the global time of an initial indexing of the whole collection. So right now we are in between 2 or 3 days for global initiation of the collection. To summarize, from the relational view, we passed to the document view of the metadata, passing through an intermediate step of JSON fragments. And here I illustrate here just for an instance simple things, elements like text associated, events, credits, and so on and so forth. I will get into more details in these fragments just to understand how exactly we are building them. And it's just an implementation of the relation between entities, so different imbrications in between the elements, which are done into a declarative way using a schema. And that allows a very high flexibility in doing different combinations. So imagine in the future, for a certain instance, we would need to, you would need to add more text or a different kind of events or some other aggregations and so on. It's enough to update the schema and then you relaunch the pre-processing phase and you obtain a richer document. This is inspired from a Jackwell project, from an open project from Google, if I'm not wrong, and that the main idea is to have something very generic and declarative. Here a simple example. For instance, in the concepts that are associated to an instance, you can extract all the text and all the values that are present in different tables of the relational database, and you can put them together and generate parts, the concept part of the final document that is stored in the MongoDB. This avoids a very sophisticated SQL query that is done again separately in this preparation phase, and it accelerates the overall process. I let you present the transformations that we do on the fly before the final version of the document.
So, thank you, Radu. So we are not just indexing our fragments once they're combined, as we saw, directly to Elasticsearch. We are doing some transformation before. To do so, we are using a library called GSLT, so Query and Transformation Language for JSON. Who here knows about GSLT or is actually using GSLT? No one. In every conference, anyone use it. We are the only ones who are using it. So you have some short description about it has been inspired by XPath and XQuery. It is just a language that we can use to query our JSON. So we want to extract some field from our JSON. We can use this language to extract them. And also we can use this language to transform our JSON. So for example, we have a string. We can use some regex functions that are proper to this language to transform, for example, the string. It's an open source library implemented in Java if you want to use it. So next time I ask the question, someone will raise in the end. And also, really important, this is a really nice feature. Its core is in Java, and we can build in Java functions that can extend the language. So in case we need to do some more complex transformation. I want to say GSLT is quite enough for itself. So if you need to do basic transformation, it's fine. It's really a complex language, then you can do really many things. But sometimes we need to do more, and so we can use also extensions. So why do we use GSLT? Well, we use it, of course, to flatten our JSON fragments because we want to reduce the necessity of using a nested object in Elasticsearch, for example. We want also to delete or redundancy. So if, for example, we have multiple fields that appear in multiple objects, of course, we want to remove that. And also, we want to group or structures, as we did in these examples, the JSON in something more readable and that contains the essential information, or at least the one that are essential for us. So this, yes. So to give you once again a short example of how this works, in this case we are just looping through an array of objects, and we are extracting only the keys that we need. So you can find, you can find the definition of the function here, and you can find also the for loop here. So, and some other function. Probably this one is some function that we defined outside from the library. So we defined it in Java. And we can also use libraries, let's say, and call a function from these libraries. So you can do, as you can see, you can do many things, and I invite you to try it. Why not? You also have a demo playground if you want to use it, to give it a try. And so, how are we indexing all this? Because we take the fragment, we transform them through GSLT, and then we need to indexing them. So we're actually using synchronous and asynchronous jobs. For synchronous, we have direct web service call, and for asynchronous, we have MQP messages queues. We have generic jobs that are defined in a declarative way, and that can be triggered. So can be triggered by us with a message sent to the controller, or can be triggered by a job itself. So we can have, for example, a workflow, what we call a workflow. Like, let's think about indexation. If we think about indexation, we may have a job that creates the index. Then we have a job that got all the IDs of the document we want to index. For example, a job that does take the IDs from the MongoDB to index them into the Elasticsearch. We get all the IDs from a collection. Of course, we can query the MongoDB to retrieve the document we want, of course. Then we have a job that does the indexation, and then we have a job that does the switch of the alias, so that position the alias on the last usable and on the last available index. And it's quite straightforward and easy to use. As I said, they are defined in a declarative way, so we just use configuration. So we just need to change the configuration if we want to do something special. To do all this, we're using Talend, which is a framework to deploy and build our jobs. Who knows about Talend? Who uses Talend? No one. So as you can see, it's quite straightforward. It's a simple console. Well, so we have our jobs ready to run. So like here, we have a job that is going to do the creation of the index. We have some parameters, like we have the alias name, for example. And then we had other many functionalities. But Talend is nice because we actually don't need to have a big expertise in development. We don't need to write a line of code to make all this work, because we can configure it in a graphical way. This is a case of an asynchronous job. There is also a way to use Talend to have a custom component in Talend and to code them in Java, so if we want to have a custom behavior. To give you an example of this indexing job, it's quite straightforward. So we get our message, we parse it, then we look for the Elasticsearch elf, if it's fine or if it's not. If it's not, we often call our DevOps to fix it. Then we are getting all the indexes. For example, let's say we want to index the event. We get all the indices that we have stored in Elasticsearch. We get the last one, so we check at the timestamp, because we want, of course, to index our document in the last index. Then we are taking the list of IIDs, the document we want to index, and we split it. We have a parameter that indicates the size of our bulk. So we, for example, if we have a parameter 500, we split it in a list of 500 IDs, and then we bulk it to Elasticsearch. And once again, we index the document and we check if everything is fine. So if things are not fine, we have an error, and then we have to understand if the error came from us, if the error came from our DevOps, or if the error came from someone else. It's often our fault. So quite straightforward. So we try to really simplify things, and we did this also with the search APIs. We are using, once again, GSLT in this case, and the idea was really to abstract the Elasticsearch domain-specific language query, because can be fairly complex. Like we can have multiple Boolean and filters at different level. So we try to find a way to simplify all this using GSLT. Sometimes it's not working because just query are just too complex to manage. And we have different, for example, we have different points for different indices. And for each of these endpoints, we can have specific functionality. So we can have functionality for the auto-completion. We can have functionality simple one for just get document by ID. And then we have a more complex one, like a full text search or advanced search. And this one is the most complex one, of course. The name, well, of course. Because we can have the business that asks us to implement really complex things for them. So to give you, to show you how this is working, this is the query that, for example, the application, the internal application from INA are calling. And here we have our transformation. So we are taking this, the interface, and we are transforming it. This is not an Elasticsearch query. If you are familiar with it, you see that it's not an Elasticsearch query, but we are transforming it into one. So we take diffusion date. So this is like an event-related filter, and we transform it into a nested filter because into our structure, events are nested to the instances. For the text journal 2020, it becomes this. So it becomes a huge, well, quite a huge query. And same thing for the aggregation. So we have two aggregation, and we just have to deal with that, creating the proper aggregation in for Elasticsearch. And once again, this is how it works. So you can see we defined a function. We define a function that is used to transform our text into something fairly more complex. Then we have a declaration of a variable. The variables have no type, so they're just defined like this. You can have numerical or string values inside. And then we are creating our query, Elasticsearch query, using the defined function, for example. So quite straightforward, quite easy to use. Then it depends by the use case, can become enormous. So the search workflow, we are using GSLT not just, as I said, for indexation. We are using it for search, but for search, we are using it actually 3 times. Why 3 times? Because we have 3 phases. So we have a first phase of query validation. Query validation, for example, when you are searching for a document, normally you want to paginate. So you want to look for the first 10 documents, and then we want to pass to the second page, and when you want to pass to the third page, well, some of our internal client, they don't like that. They want to retrieve 10,000 documents or even more altogether. And so we had to create this query validation to avoid them this possibility. So if they ask for 10,000 documents, we just say, no, you can't. So query validation is for this, and also to be sure that the structure of the document is correct and to be sure that everything is set well. Then we have the query transformation, that's just what we saw earlier. So we are just taking the query, validated query, and we are transforming into the Elasticsearch one. We send the query to Elasticsearch, we get the response, and once again, we use the GSLT to transform the response. Because we want really that our internal clients can use the Elasticsearch answer, and we want to clean it, essentially, so it's easier for them to use it. And I'm going to let Radu talk about this.
Yeah, a quick word about the architecture, just to have an idea how everything fits together, because we talked about different things, models and transformations and everything. But in one schema, you have here from the application on the right side, this is an internal tool, for instance, where the archivist, documentalist can prepare their queries and they can work on their documents. And on the other extreme, on the left here, you have Elasticsearch cluster, where we have our indices and where the queries arrive. So all this part in the middle, it's our infrastructure for the data lake. It communicates with these very simplified search APIs. So that offers a very simplified view on the content and on the definition of the rules of the search engine. And everything here managed by Kubernetes are microservices that are very easy to deploy and to configure. That's a solution that we came up with, and the best thing of it is that everything is based on resources that are loaded on the fly. So we don't need to compile everything if needed, or if we want to add another search case or another functionality, or if we want to modify the implementation of the search. So everything it's done inside these resources, which basically are JSON documents that define how the queries should be transformed and interpreted, and they are used by small Spring Boot instances that they will effectively execute each and every query. And then a classical communication, HTTPS, in between the search engine, each microservice, and we have also this part of the controller. It's a proxy that first of all exposes different APIs, for different users, different categories of users. So it also gives an order of execution and of treatment of each query. What we did after the first experience of indexing everything, and of course we wanted to have some good performances also for the search point of view. So not only that to ensure that everything is stored in the search engine, but also to have good search performances. We used a Neoload platform that's very convenient for simulating a large number of users with different complexity of the queries. Can be a simple full text query, and on the other extreme we could have a very complex Boolean logic of filters grouped with different aggregations, different levels in the aggregations and imbrication of that. So things could be very complex at some point. Overall, for the search performances, we experienced less than 200 milliseconds in average for an average complexity query, which is quite acceptable for the use case for an internal application. So it's not a web server opened to a large public. And I already mentioned for the indexing process, we managed to index everything, all the 50 million documents and more in 2 or 3 days maximum. Just a screenshot of the neoload evaluation. What we did here, and that was the confirmation that our performances are good and are stable. On top here, you have the number of users. So we started with 100, and then on several thresholds of 20 or 50 users more, up to 400 users. And here in green, you have the response time, the number of queries per second, and in yellow, the response time, which is rather stable, which with different variations according to some the complexity of the queries. Probably here there were some more complex aggregations that were executed, but globally speaking, we have a flat line of response time. So we were happy with that because the goal is to maintain a good performance in the perspective of the increasing size of the data as we collect more and more each and every day. I will conclude with 4 or 5 takeaways that I would like to point out. So even if our project, maybe it seems to be a big puzzle with different technologies, different aspects, we experienced different challenges, and we learned a lot. And that's what we wanted to share with you. So the first thing was related to the data model, the fact that we implemented a graph of entities, and not only that we take everything together, but we decided to split this graph based on functional views. The second thing that we talked a lot are these JSON fragments, which was a necessary optimization to ensure a good performance in terms of indexing. JSLT transformations, because it's a very light way of transforming documents and to adjust them to your needs if you want to store complex documents in Elasticsearch or any other search engine. Also in the transformation of the queries, that's a very interesting aspect, because you don't have to when you collaborate with different other teams, with different other projects, they don't have to have a high expertise in search engine or in Elasticsearch queries to be able to interact with the search engine. So you can confine everything under these some generic APIs. And the last point is related to the relevance of the search. This is an ongoing work right now, but we already have some good feedback, because the application is already used for several months already. And we didn't mention here, but our next step, it's already initiated, and we integrate semantic search on top of the full text search that we currently have. So we are heading towards a hybrid approach on the search, and we are looking forward to see how it performs and how much we are able to improve the user experience with semantic search. It's a very difficult topic, but we are happy that it gives us the perspective in enriching our solution. So with that, thank you for your attention. We hope that the subject was quite interesting for you. If ever you have a subject or a project related to these topics, we are very happy to exchange with you, and maybe we will get some more ideas about different things that we can optimize. Keep in touch with us, with our team, and thanks again for watching.